to Science Buzz Cafe number 174. Before we get started, though, next week is Dragonfly Lady. Not Dragon Lady, no. It's Kathy Biggs who talks about the dragonflies and damselflies of Sonoma County. I have not met her.
I love dragonflies. She's darling.
But I heard she is fantastic, though. So
knowledgeable.
Yeah. So dragonflies, and I don't know how they fly backwards, but apparently they do.
Well, we'll have to dress appropriately.
That's intriguing. Okay, everyone dress up as a dragonfly or damselfly. But before we start tonight, I thought we'd do a little quiz like we did last week. It was kind of fun. You missed it.
I did.
Yeah. And we give out chocolate, and serious chocolate, let me tell you.
Whoa.
They charge a lot for this chocolate. It's from the chocolate... What?
You give booby prizes?
No.
No.
Is it too expensive?
It's from Sonoma Chocolatiers, downtown near Whole Foods. Those guys, handmade truffles. So I have 3 questions and 3 truffles to hand out, just to kind of warm us up.
Daniel, how do we have to answer to get a truffle?
Correctly.
First, raise your hand and I'll choose who gets to answer. I better do it that way.
I guess you're not getting a truffle.
What about nepotism? What are the rules here?
There are no rules. This is total experimental. What are the oldest known objects on the Earth? Raise your hands if you know.
I have to think about it.
Think about it.
Oldest known object.
Somebody already said stromatolites.
No, that's not the oldest.
Would you define
I'm not to
object?
your question yet.
Would you define object?
Yeah.
Physical substance, no matter how big or how small.
Okay.
So the Earth would be one answer, but that's not the one we're looking for.
Peter!
There are diamonds that are inside of meteorites. They're called carbonates or something like that, and they predate Earth by billions of years.
That's not the right answer, is that?
That is a answer. It's very specific.
Well, no, hold it. Don't say yet.
Oh,
that's the wrong answer. That's not what we wanted. It doesn't matter. We don't want
Wrong, it's just not the one you want.
It's not politically correct. Okay, you'll split the chocolate. We'll have to split the chocolate.
Yeah, he was more specific than my answer. I mean, he knows.
Give the man a truffle.
Okay.
Give the man a
Are they
truffle.
give the dog a
There,
bone?
wait a minute, let me just say, there are pre-solar grains. Oh, we're going to get another one.
We're trying to work this a little bit.
Zircon?
No. You get his chocolate goes to.
Zircon and
Robert.
tweezers?
I was guessing zircons also.
Well, Peter's got it so far.
Larry King.
Pre-solar grains.
Well, right.
But he was right. That's nanodiamonds.
Well, explain this to us. How was Peter right, and this other answer is also right?
Well, yours is more general. There are 10% of the mass of the galaxy is dust, and when the solar system accreted, something like, say, a supernova shockwave caused the dust to start to condense and collapse into a cloud. And it got heated and cooked up into what's now our solar system. But out in space, to this day, there are grains that are billions of years older than the solar system, and you can find them in meteorites and extract them. And it's a whole discipline of science.
Is this what you mean by older than dirt?
Older than the Earth, older than the solar system, older than you, Robert.
Older than dust.
Older than...
Later we'll get you know.
But the diamonds are very cool. All right, next question.
Right, next question.
What good is it?
Yeah, what good is a diamond anvil? Raise your hand if you might know.
There's an answer.
It's a great way to exert pressure on a test specimen.
He gets it, doesn't he?
Extreme pressures, like Jason.
I'm not a scientist. Jeez.
How about if you're making little shoes for gnats?
So you can explain that a little?
Yeah, they get gem quality diamonds with flat tips. They set them up in this apparatus. I'll show you a picture of one. And with a little gasket and just a little bit of powdered material that they want to usually oxidize. They want to see how it behaves under extremely high pressures. And then they crank it up and they shine a laser right through the diamonds. Works nicely that way, and they can
Heat it up.
They can look at the phase changes in the mineralogy of the lower mantle, 2,000 miles down.
Good job, Dick. Okay, one more question, and then we'll get on with it. What is the oldest life form known to women? Easy, we're politically correct here.
Archaea.
The bird.
I didn't write that question.
When you say
Oh, shoot.
What?
Hey, stromatolites.
What?
That's the oldest.
Susan, what do you think? So can you show us your little thing quick? The reason we have this question is because Susan just came from Australia, and yes, you won the job.
No, 5 years ago.
5 years ago, close enough.
What did he say? I have a 3.5 billion year old sample of a stromatolite.
Can we pass it around?
Yes.
3.5 billion.
3.5 billion years old.
That's-
And each hand that goes on it is very special.
Is that male or female?
Stromatolite.
What stromatolites are the bacterial
No,
mass.
no, no, it's from the heart of Australia.
And what is
From the very heart of Australia. It is a
Okay, you pulled the
stromatolite.
can.
It is one of
You ate
the
it already,
earliest
huh?
forms of life on planet Earth.
But it's
It
not
is
the earliest.
3.5 billion years old. And the Earth is 4 billion years old. So it came into being, and it helped to get rid of the iron ore and create oxygen.
really?
Yeah, it really
And you
are.
can see how heavy that little tiny piece of rock
There was
is.
a stromatolite Al Gore and nobody listened to it.
In Australia, it's the very heart of Australia.
What they are, it's a sedimentary rock that forms from bacterial mat. And the bacterial mat causes sediment to accumulate, and it keeps growing, and the sediment keeps accumulating, and they give these characteristic bulbous forms. There are living ones today in places like Shark Bay in Western Australia, which you can see. There are numerous photos of them. They can only be in saline environments where there are no grazers that would munch up the bacteria. And
Were they the ones that created the oxygen, or they followed?
well, they would have helped. They would have been part of the process.
But they were, the ones today are not one of those, right?
No, they're I believe, it
This
is
is
thought
where
that
I
they
got
were.
So the stromatolites were eukaryotes?
Yes. No, they were prokaryotic, but they would have.
Cyanobacteria.
Yeah, I think there's cyanum. I don't know.
There,
there's, yeah.
They're rough. You can't tell.
there is bacterial and non-bacterial stromatolites. And there is the time span when they went from non-bacterial to bacterial. And this one is supposed to be 3.5 billion years old, which could be the non-organic stromatolite. But I don't know.
You mean inorganic?
Inorganic versus organic.
The mysteries of science. I love it.
I mean, when you go back 3.5 billion years.
None of us were around then.
How do you date it that old?
You've got to find some radioactive materials. It's a whole art of dating radioactive materials.
One
Just a little bit.
last piece of business, and this is important, so pay attention. To all you NASCAR fans, I have 2 tickets to NASCAR tomorrow.
Where is it?
Looks like 3.
What's that place? Sears Point.
South of Petaluma.
Called Infinity.
You're not just-
Okay, I tried. Anyway, Richard, let's start.
All right.
And we'll take a break. You have enough material. We'll take a break and then come back.
This is how that is.
Okay, from dust thou art, and that means everything. I spent an afternoon raiding the digital archives of Scientific American, getting all these pictures that I'm going to show you. And here's a life cycle of an interstellar grain floating out in the void, and they have a rocky or a mineral core and kind of a crusty organic gunk on the outside, and they float around and they change over time, and then eventually they get sucked up into a planetary nebula. Here's some of the pre-solar grains that are floating. These have been extracted from meteorites. What you do is you take a meteorite and dissolve it in acid and look to see what's left over for these very refractory oxides. So there's a diamond. Oh, let me get my pointer. I forgot my pointer. Can I work with my pointer? But those are examples of the pre-solar grains that have been extracted by digesting meteorites. So there, as you can see, the diamond lattice. Very small. I read an article back in the 90s on this subject, and they had, they can date these things, and they had some oxide grains that were, in their estimation, formed in a red giant, like Betelgeuse, only long ago, 6 billion years ago. And that just blew my mind. You know, it was smaller than a pinhead, but 6 billion. Very, 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 very cool.
Diamonds forever.
Very cool.
So here we have the Orion Nebula, and this is supposedly a solar system in formation in a giant cloud of gas.
Wow.
And someday there will be a sun and planets and the whole deal. So I'll take you through the what is thought to be the growth of the solar system. So here we are at the cosmic dust bunny stage. I like that. The protosun's in here. The Earth would be right about in there. And an astronomical unit is the distance from the Earth to the Sun. So this snow line right there is where the all the volatiles have been driven off from close to the Sun. So this, our snow line in our solar system approximates the asteroid belt, which are rocky objects, but you go out one step further and you come to Jupiter, which is a gas giant. So the inner planets have had their volatiles driven off during the time of formation, and any volatiles present, like water, potassium, the alkaline metals, carbon, oxygen, all that. Well, oxygen, and oxides would be here, but the more volatile materials came in late. So here we go. Here we've got a sun starting to form. Here's a baby giant planet sweeping its orbit. It's deformed, it's spinning so rapidly. The next stage would be literally hundreds of, it's called oligarchs, Moon to Mars-sized objects all spinning around and gradually coalescing into larger bodies. Much of this is based on computer simulations, and you know, it's all revealed knowledge as far as I'm concerned. The models are as good as the computer and the programmer. So here's another part of the simulation. The next step is the formation of a gas giant like Jupiter. Now, I know if you've been looking at all the material coming out about finding planets on other solar systems, the Kepler telescope now is producing amazing results. And these giant planets are very common. And a lot of them are very, very tight orbits, so they spiraled in very close to their sun, such that they may revolve around it in a day.
Does that mean, excuse me, does that mean that the giant planets in our solar system are going to be spiraling in too?
Well, they've settled down where they are. They actually moved out. Saturn, Neptune, and Uranus moved out. And they are, I'll get to that.
Richard, did that say unbalanced torque?
Yes, it did. The way it's moving through the gas gives it, slows it down. They tend to spiral in. Gus?
If our planetary snow line, so to speak, is the asteroid belt, and these big, giant gaseous planets are even close, does that mean their suns are not as hot as ours, or?
Well, I'm going to get to that. The early sun was extremely hot. It was called the T Tauri state, and I hope I'm pronouncing that correctly, Tauri. And it was the first million years or so of the sun's life, it was smoking. Smoking. And it drove all the volatiles out of the inner solar system. And then it calmed down to the point that it was 20-30% cooler than it is now, in the Archean, and it's gradually warmed up ever since, and will continue to warm up, I might add, to the point that we'll all have to be living underground 200 or 300 million years in the future. I'm sure we'll make it. All this was pillaged from Scientific American. This is from a Nature article. This shows the refractory elements that would crystallize out of the gas cloud at very high temperatures, 1500 degrees centigrade. And here the alkalis, the chalcophile elements, sodium, potassium, manganese, gold, germanium, what have you, at lower temperatures. Then we have lead, indium, tin, cadmium, sulfur, and even this group, even lower temperatures. And finally, you've got oxygen, mercury, carbon, nitrogen. So when the sun was really hot, all this stuff was driven out of the inner solar system. And as the Earth accreted, now this diagram shows there's temperature on that axis, and this is the fraction condensed of the planet. So you get the highly refractory elements in that these guys early on, but they don't produce a lot of mass. Oops. And these guys, well, no, that's all lumped together, yeah. And then these guys come in there, and then the sulfides. See, as temperature's dropping, you get the lighter and lighter weight, or less refractory elements.
So it's like distillation in reverse.
It's like distillation in reverse, yeah. So this is an early solar system chronology. 0 is the formation of the thought to be the formation time of the solar system. They're the oldest objects. I've forgotten the acronym. Carbonaceous, carbonaceous aluminum, something inclusions in meteorites, and they're the oldest thing we can find. And so we've got 65% of the Earth formed here. See, we've got meteorites from Vesta, chondrules, cores from planetesimals, all this all these dates from meteorites. And best guess is most of the Earth was formed around here after 45, see there's time right there, 44,570,000,000 years, 60 million years ago. Here the sun is starting to light up right here. Fusion begins. And then we got the moon forming impact right there at about, that would be about 45, 30 million, 4,530,000,000 years ago. And that kind of reset the clock on the planet. So what's believed to have happened is, and this is the ruling hypothesis, it's been this way for decades now, that a Mars-sized body, one of the very last of the planetesimals, impacted with the Earth, increased its angular momentum tremendously, and gave it its axial tilt. And the moon, what became the moon, splashed off after the impact, and the moon was largely formed by the impactor. What this shows, this is the only figure I could find, these are the lighter isotopes of iron, and they were preferentially lost to the Earth because of their lighter mass. And so there's subtle differences in the chemistry of the moon rocks and the Earth that are what gave rise to the hypothesis of the giant impactor. And it's been named Theia, T-H-E-I-A. That's the goddess who is the mother of Selene, the moon, and Titan. So after the impact, we had a magma ocean. That's that. With droplets of metal sinking down, forming a liquid metal pond at the base of the magma ocean. And you have a silicate mantle like we do now, and then these droplets would coalesce and drip down through the mantle, sinking to form the core. And because you're conserving angular momentum, there was a lot of heat released in this process, so that it tended to keep the Earth hot and molten forming the magma ocean for tens of millions of years, probably. It's no one was there, so we're all model dependent here. But the magma ocean didn't last for a long, long time because convection is in a fluid is a very efficient way to remove heat. Convection through solid rock. Rock's a great insulator. If you have an underground house, once you get it warmed up, it's going to stay warm. So the infall of the core helped keep the upper the magma ocean going for somewhat longer. So again, you've got the core, you've got a silicate mantle, this liquid metal pond at the base of the magma ocean, and a magma ocean on top.
Question?
Yes, please.
I'm confused about what you said about the core. It almost sounded like you said it didn't form until after the impact it formed the moon.
I think that the core pretty much dates from the impact.
Huh.
At least they use hafnium tungsten. It was something I didn't get to before this talk, but there's you can date core formation by the tungsten isotopes, and I'd have to get back to you on it though. But the core formation pretty much is dated to the giant impact, which in this guy's estimation is 30 million years after the, and see the T-Tauri phase where it was just blazing hot. A lot of that was due to the contraction. Fusion hadn't started, and that blasted all the volatiles out of the inner solar system. You get the giant impact in here, and then what's called the late veneer. in here, and that's all carbonaceous, chondritic, stony meteorites, prodigious numbers of them, and that's when the water came in. That's when the volatiles came in. And the date, if you look at the iodine, xenon, and uranium lead dates, are all 100 million years plus or minus younger than what we know as the age of the solar system. So what they date is the late, what's called the late veneer. So at 4.4 billion or thereabouts. Yes, Dixon?
Does what you're saying imply that planets that didn't experience a big impact wouldn't have a core like ours, and therefore maybe wouldn't have a magnetosphere like ours?
Mercury's got a major core. That's the densest planet.
Are we assuming that came from an impact too, or
No, I think Mercury, being so close to the fire, just, you know,
melted down there?
yeah, it got a lot of the volatile material still distilled off it. Venus is a whole nother matter. There was a giant resurfacing event 600 to 900 million years ago, and the whole planet got resurfaced by volcanics. Nobody knows why. I'm sure there are
Parking lot.
But this is what's called an isochron, and right there at 4.4 billion, that's the age that the that's a Canyon, I think it's Canyon Diablo here, right there. But that's the age of the resurfacing event, the late veneer, rather. Origins of water on the Earth. So, fancy picture. I like Scientific American. It used to be thought that it was comets that brought it in. Earth has basically 2 oceans worth of water. One ocean and groundwater and a few other things, and another ocean's worth of water down in the mantle. That's been subducted down and then comes back up in volcanoes. But when they sent the probes, they sent one to Halley. Where else did they send one? They looked at the deuterium hydrogen ratios in the cometary material, and deuterium's heavy hydrogen. It was formed in the Big Bang. So what you see is what you get. There's no new deuterium being made. And the deuterium hydrogen ratios were distinctly different from what's found in, say, the Earth's oceans. So it seems to rule out comets as the primary source of the water on the planet. But carbonaceous, chondritic meteorites, comets, bodies like that, not icy comets, but solid asteroidal bodies, could have provided all the water with no problem, and the other volatile elements that we have on the planet.
Where did they get the water?
They would have come from the outer solar system beyond the snow line. And the outer planets, the big guys, would disturb the situation out there. And it took the solar system a long time to come to equilibrium. It wasn't until well, let me get to that at some point. Here's another one. I love it. Wham! Here comes the ocean. So here's the late heavy bombardment. I don't expect you to be able to read that, but there's 4 billion, 3.8. And what they found when they went to the moon and they brought back samples, and what somebody did is a really elegant paper. He took 100 grains of moon dust and dated them, ran them through a mass spectrometer and dated them. And you could see, he did histograms, and there were these peaks. And there were a lot of peaks up to 3.8 billion years ago. And what that gave rise to is the late heavy bombardment theory, that the whole inner solar system got clobbered toward the end of what we call the Hadean period, from 4 billion to 3.8 billion years ago. And it was theoretically difficult to understand back in the 70s because it was thought that it should have been swept clean of cometary, debris by that point. But when they did the dynamic modeling of the evolution of the gas giants, it turns out that Saturn, Uranus, Neptune have moved out into what we call the Oort cloud, the halo of icy debris, chondritic debris that surrounds the solar system. And they destabilized the Oort cloud and sent all these thousands and thousands of bodies spiraling in to clobber the inner solar system. And that's called the late heavy bombardment. And you look at the Moon, Mercury, parts of Mars, and crater. And Earth, big time, crater, yes.
You speak of years. What is the definition of a year at this time?
Well, we're using our years.
Our
year.
So
We're
the
using
rotation.
We're using a year in probably seconds would be the 10 to 15 seconds. I don't know, but the actual rotational or the sidereal year has been slowing down due to the interaction with the Moon. We have really good evidence that there are 900 days in the year, 900 rotations of the Earth on its axis, in a year that's as long as our present year, plus or minus a little bit maybe. So however many seconds that is. But the Earth has been spinning down and is continuing to, and it caused problems with the atomic clocks and the there's this whole issue: do we reset the clock or do we just let it drift? And the astronomers wanted to do one thing, and the airline industry wants to go the other way, and but they're always having to tweak the year by 1,000th of a second every now and then because of the spin down. And then there's a big earthquake like the one in Japan. That'll change the length of the day.
Why did Neptune and its neighbors move out to a farther
because the mathematicians tell me it did.
I see.
It was dynamically unstable, Robert.
Well, did it happen gradually, or did some event cause it to move out?
Apparently, they gradually migrated out. But planets, the orbits of planets, when you start out, are not set in stone. So they're always doing this dance. Like the reason there's no planet where the asteroid belt is that Jupiter didn't let it happen. It interfered with the planet forming process. Mars could have been bigger, but it wasn't, probably because of Jupiter's nefarious influences.
But the moon caused...
Nefarious, that's a term of art.
But the moon caused the Earth's rotation to slow down, did it not? The internal friction from the tides and whatnot.
I don't remember that. It definitely added a lot of angular momentum, so I would say it sped it up. But it gave it the axial tilt. And the great thing about the moon, I mean, the moon is absolutely vital. Mars does these kinds of things, 45 degrees over. Can you imagine what the year would be like if the Earth wobbled over 45 degrees? What is it? Is it Uranus? It's right in, it's got its rotational axis in the plane of the ecliptic. Good Lord. It wouldn't be good. Well, the moon stabilizes. It's like the whole system, the Earth-Moon system, is stabilized by the presence of the moon, so that our axial wobbles are just a few degrees rather than 45, 50.
But the moon's falling into us.
But the reason the moon always faces us, is it not? Because it has slowed down the internal heating caused by the tides and whatnot, and so the Earth
it's bulging toward us now.
Right, but the Earth has supposedly slowed down.
And the Earth has slowed down too.
But when did you say the moon impacted us? When did
About 30 million years after the formation of the solar system. And that was the last 10%, and then you got a few more percent with a veneer at 100 million, and then, you know, whatever, in the late heavy bombardment. But the moon, the Theia, was about the size of Mars, a little bit bigger, maybe.
Is this part?
That's the way it works.
Is this part of an anthropic effect? That we have seasons and things
We've
that
got a
work
great
for
planet.
life?
You know, it's really designed to have life. You know,
Who designed it?
deluxe
This is for Dixon. Who designed
That's true.
I want my money back, Daniel.
it? Oh, good. Thank you for paying.
I did already.
I didn't say God did it. I said this is a great planet, though.
No, it is. It's cool.
Accidental design. I love it.
Yes.
That's what around works.
Joe?
Richard,
Yes.
what is the explanation for rotation?
Well, as the dust cloud coalesced,
And another thing,
Wait
does
a
everything
minute, you get
rotate
the answer
in
to
the
that?
same?
yeah, if you were looking down on the North Pole, it goes counterclockwise, and the whole solar system, looking down from the North Pole, goes counterclockwise.
And the basic reason is?
Distribution of angular momentum in the primordial dust cloud. Robert, help me here.
But they don't all go the same direction, do they? All the planets.
How about
Yeah.
angle?
Yes, yes.
Yeah, they do.
Excuse me.
Now, there are some small moons. I seem to remember hearing some of the small moons of Saturn or Jupiter go the wrong way. Has anyone heard that?
Yeah.
Venus goes the opposite direction.
Who does?
Venus.
One of them does.
Really? It does?
Wait.
Goddess of love is
Just like
perverse.
the
Same direction around the sun, is what he's saying.
No, it's the same direction around the sun.
Well, they do computer simulations of the accretions of galaxies and whatnot. They assign all these supposedly random distributions of mass.
Yeah.
When they just let time go on and it begins to swoop in, they automatically start turning some non-predetermined direction. It's
Yeah.
just, as you say, it's just conservation of momentum. And everything else follows suit.
Yeah.
Once you start that mess, it's the way it goes.
You know it's not uniform, and it's going to be a little skewed one way or the other. And when you collapse a body that's, I don't know, a light year across, whatever it is, and sphincter it down to, you know, the size of the solar system, there's a lot of momentum there, and it's going to spin
Gravity
up.
increases the spin. We learned that from Richard Boyd.
Does the moon have a core?
Have what?
Have a core? Does it have a...
Not an iron core.
It does, but there's not much of one.
How do you explain that?
Because most of the Thea's core got left behind during the impact.
It's on Earth.
Yeah.
Doesn't Mercury have a strong magnetic field?
Yeah, I think it does. It does have a field.
But the
It's got
moon
a
doesn't,
giant
right?
core.
But the moon doesn't have a magnetic field, is that right?
It's got precious little. I think there's, you know, something you can measure, but that's about it. And that's the other. I'll get to the magnetic field later. Let's get off this. Oh, this is a nice one. So here's a cutaway of the Earth. We live up here.
Thank goodness.
This is where all the action is. There's the lithosphere in the upper mantle. Called the transition zone. As you move down through these layers, I'll show you a blow up. The minerals collapse into denser forms. So olivine will go into a spinel mineral, which is basically olivine is an iron magnesium silicate, MgSiO3, something like that. It's the green sands of Hawaii. If anyone's been to those green sand beaches, ubiquitous mineral in basaltic lavas, very, very common mineral. Well, it collapses, and then here in the main body of the mantle, it goes to something called perovskite, which we don't see at the Earth's surface, and that is a even denser lattice form that stands up against the immense pressures. You get all the way to the bottom here, and there's something poetically termed post-perovskite, Nobody knows what it is. There are, you know, papers written on it, and they've identified it by tracking seismic waves that strike glancing blows and are refracted off the core mantle interface. And and then we've got the core, the liquid outer core, and then the solid inner core.
The yolk.
The yolk, yeah. Like the central realm of the densely packed, if you ever read Timothy Leary's Book of the Dead.
The central.
I didn't know he wrote Book of the Dead. I thought the Tibetans did that.
Well, he did the edition that we all used in 1960. I'm not going there any further. So here's a profile going through the Earth. It really should be pie-shaped, but it's not. So here we have the upper mantle, the mantle, the outer core, the liquid core, and the inner core, which is solid. And you see these are shear waves. The shear wave will only go through a solid. So you see no shear waves in here because it's liquid. Shear wave will go through, you know, anything solid, and you induce a shear wave by banging something. So the shear wave oscillates across the direction of propagation. A pressure wave, a P wave, primary wave, whatever, a sound wave oscillates in the direction of propagation. So it goes through solids, gases, liquids. So these are the velocity profiles that the seismologists have worked out. And here's the D prime layer, the post-perovskite layer, and they figured out through very elegant techniques in the 20s, a Danish woman seismologist whose name I forget identified the inner core as the last major part of the Earth to be identified. Well, I guess maybe this layer here is, you know, up for grabs, but that's how seismologists understand the Earth. Ah, the diamond anvil. So here we have it. Gem quality, nothing but the finest diamonds, and they lose a lot. The diamonds actually deform in some of their extreme tests. So you put your mineral material, whatever it is you want to evaluate, just a speck of it, but that's trillions of atoms, so it's plenty, in this gasket here, and then you crush it between the two diamonds, and then you can, because diamond is a transparent material, you can shine a laser through it, and you can heat it, and you can evaluate the changes in mineralogy. So that's what a diamond anvil is good for. And they've been doing this for 30 years now. So here we're looking at the bottom of the mantle. Here's the top of the core. We have these dregs sinking down, piling up. Who knows what they are? Post-perovskite, very dense material. This is an area of active research right now. Every time there's a big earthquake, and you get a whole bunch of ray paths, and you've got seismic stations in the right location. They look for these grazing wave paths, and they tell you, hey, what's going on. My son does this. It's revealed knowledge as far as I'm concerned. But,
What's
so
that mean,
this is
revealed
one of the.
knowledge?
This is a schematic. The baby Earth core is liquid. It's not teenage Earth. You're starting to grow the post-perovskite layer. Mature Earth, we've got the post-perovskite layer, and there's the lithosphere out here, and the upper mantle, and the inner core. So Let's throw it in. The magnetic field. This is cool. All right. So the magnetic field. We could not be here without the magnetic field. We would be dead. Our DNA would just be no good. And this is a map of the conceptual diagram showing the field lines. And I'd say that's north. That's cold. That's south. And this gives you an idea. And you can see they're really tangled. But if you've ever done the experiment where you had a magnet and you sprinkled iron filings and you could see the lines, that's what these are. And the magnetic field of the Earth keeps the blast, the dangerous radiation from the sun from getting to the Earth, except when you have a magnetic reversal, and that's the problem. So here's a series of mathematical models of a pole reversal. And in this one, they said they're having it take place over 1,000 years. And see, this is in this model, you've got several poles. It's either a quadrupole or what have you. The whole dipolar field breaks down and reconfigures with the north and south poles reversed. And this was worked out in the 60s and 70s. The magnetic striping on the sea floor was identified as being the basalt crust of the ocean floor had alternating north-south dominant polarity, and now it's understood in great detail the polarity reversal history of the Earth, and the question has been what takes place in a reversal, because we haven't observed one. We do know that the strength of the field is declining. You can take ceramics from any historic site, and because they've been fired and cooled, they take on the strength and the orientation of the magnetic field at the time that they were fired. Of course, the pots move, so you don't know the direction. You do know the strength, and you can see that the field is distinctly weaker than it was in Roman times. Now, whether it's going to go to zero and go on through or not, we don't know. But back in about 12, 15 years ago, I read a paper where they had dated a magnetic flow, magnetically sampled a lava flow at Steens Mountain in Oregon. And they took multiple samples from the core of it to the chilled margin, and the core had reversed compared to the margin. And you can pretty accurately say that based on the thermal properties of basaltic rock, that if that reversal did take place, as it seemed, it took place in a year, which they don't want to believe, but it's pretty interesting. That would be great as far as we're concerned, because we wouldn't have to deal with all that incoming solar radiation. Not the light, but all the protons and general...
I plan on working on my tan.
Yeah, just the solar mass ejections, and here's the Earth, here's our field protecting us. But there's in the 1850s there was this big one that took out the telegraph net and produced a giant solar mass ejection event. And a lot of the very early, they set up telegraphs across the U.S. and they got impacted severely. They had aurora, I'm told, in the Virgin Islands.
They set telegraph offices on fire.
They what?
Wow. Set the telegraph offices, some of them, on fire.
Whoa.
I Googled it.
Nice. Anyway, so here I think they've shortened the scale here, but here comes the coronal mass ejection. It's heading our way. We just missed having a big one a year or two ago. You know, it's like it went that way and the Earth went this way, so we missed it. But the next time a big one hits us head on, I wouldn't want to be in the space station, or there are a lot of satellites are going to go. They had one in the 80s that took down the grid of Quebec because the ground there, the Precambrian rocks, are very good insulators of electrical currents. So instead of the currents being dumped through each tower, it built up and fried the system. Anyway, it's fragile.
What did that do to computers?
Well, I hope my surge protector works.
Actually, this is a big deal. There's a conference right now going on about space weather. It's a big deal.
Yeah.
And they can actually do 3D animations of what these mass ejections will do. It was in the New York Times, I think, Tuesday.
Yeah, Ulysses satellite will give us a day or two's warning, unless its budget gets cut.
So you turn things off quick.
Yeah, turn everything off.
When was the last magnetic reversal?
About 700, what was it? I think they're saying 780. They keep moving. It's a moving target, but 780,000 years ago. Now, there were some smaller ones where it tweaked for 10,000 years and went back. But the big one is called the Bruns-Matayama. And that we use it's a golden spike, because you can find that in Quaternary Pleistocene sediments. And for example, there's a site in Galilee, Homo erectus site, which boggy sediments formed along the river down there, and they chose the horizon, the interval, to excavate and sample because it was right at the reversal, so they knew how old it was. And what they found was use of fire. They found fireplaces with burnt wild grains, and they found living floors where they had gathered vegetation to sleep on. They had living areas. They cooked and had a fire over here, and they slept over there. They were
on their way.
So living people back then just cruised right through the reversal. There wasn't any big impact.
Well, we don't know. I mean, maybe.
I mean, did
no, it didn't. No, the reversal. There have been so many reversals, and they don't. They look for extinction or speciation events. They're hard to find. They're hard to find. But the thing about Homo erectus, which I find fascinating, is they used fire, and they sculpted their tools with an aesthetic eye. They were more than strictly utilitarian. They had you see some of these Acheulean hand axes, I've got several. They're nicely formed. They really are. Joseph Campbell pointed this out in his Way of the Animal Powers encyclopedic volume, that he has a picture of one in there. It's just gorgeous. I mean, somebody went through a lot of work to make that thing look good. And it's, show you, 1 million years old. I mean, that's not an animal. Or that's a very cool animal that's on its way to being us. And fire. What is it? Rudyard Kipling
Above the wheel.
What was it? Shere Khan, the tiger, faced the fire, the kid could, Fire is, we're fire, and we're beauty.
Did you say that they don't find any correlation between jumps in evolutionary rate with magnetic reversals of the...
They look pretty hard. If anybody has done it, it's got by me. I would go, oh yeah, if I saw any reversal, maybe some snails do something, but... So here's a speculative atmospheric history showing 4.5 billion there. I don't know what's going on there. We got water in the atmosphere, and it drops out, carbon dioxide, mostly nitrogen, some methane and ammonia. And then about 2.5 billion years ago, we get the rise of oxygen. And that's pretty much the story, and it's life that did that. But life took all this time in here to get rid of the ferric iron in the oceans. There was a huge, the oceans were buffered with vast amounts of dissolved iron oxides that had to be stepped up a notch and turned into rust. And those are the so-called banded iron formations, very common in Australia, northern Minnesota. They're beautiful rocks, and they're layered sedimentary rocks that are basically precipitates produced by oxygenation of the ocean waters. There we go. Here's one of the Jack Hill zircons, showing what they look like. That thing is probably not even a millimeter across. And 4.4 billion. Oldest object of this Earth, but not a pre-solar grain that anyone's found. The Earth was, 150 million years old at this point, and they know from the oxygen isotopes in it that it had a cool surface that could have had liquid water. If there was magma ocean was over.
Richard, when did those meteorites arrive from Mars?
They've been seen to fall.
Are they still coming?
I know. I was reading an article where they looked at some aspect of the chemistry of a Martian meteorite that, quote, had been seen to fall, so they knew it hadn't gone through a lot of weathering and alteration. But I think the original of the type is a Nakalite from Egypt.
Do they know how old they are when they left Mars?
They know all that. They know how long they spent in space in transit. They can tell that. Allen Hills 890001, that has carbonate in it. So it was not shocked so heavily in the exit that the carbonate was destroyed. And the numbers I remember, dredging them up from the bottomless pit of my mind, maybe 10, 20 million years in transit.
No.
As you know, the Antarctic meteorites are just great because they land in the ice, they get frozen, you don't get a lot of dirt on them and schmutz and all that. And there was that other one that fell, a carbonaceous one on Tagish Lake in British Columbia. They got it before it disappeared, and that's very, very interesting, very carbonaceous meteorite. So here's a zircon.
Richard?
Yeah.
Quick question for
Yes.
you. When those things were first announced, they were talking about there was evidence of early life, and then it was poo-pooed.
It's poo-pooed. It will be poo-pooed forever.
Do you think? Is it?
I found it fascinating. I said, hey, this is very, very cool. But this is the kind of thing that somebody who's at the edge of retirement will publish, so that he does not destroy his career.
Gotcha.
What's the nature of that meteorite that the Arabs make such a big deal out of?
What's his name? Idris Shah has seen it. He described it. He says it's a black rock. But they're not letting us take any samples back to the lab. I think they could kill you. A bunch of losers. We want to know. But it was a pagan. Shrine before the Muslims took it over. And there are also examples in the Greco-Roman in altars. In altars.